And we now have a slightly shorter talk, but with double the speakers. So Sacha-Élie Ayoun and Xavier Denis will talk to us about hybrid verification for Rust.
Thank you. So as Jules says, I'm Sacha.
I'm Xavier.
And we're going to give a hybrid talk about hybrid verification for Rust. So I'll be giving part of the code, there will be part of the talk, there will be giving the other parts. And we're going to advocate for what we call hybrid verification in general. The point is, in the recent years, developers have starting to accept that they can change the way they write code to satisfy a type system. People have started doing TypeScript even in the JavaScript environment. There's this higher thing for Python, and there's a billion Python type checkers. And of course, there's Rust, which has a very, very strong type system. And system developers are happy somewhat to write code that satisfies the type checker and the borrow checker. And the question is, how long have we been waiting for this to happen? We've been waiting quite a lot. And the second good thing, as you all know, is that these languages have solved the problem of program correctness. And thank you for listening to my talk. Right. They haven't solved correctness, but they did make it a lot simpler to write correct programs. And what we're trying to say today, what we're trying to advocate for, is that these languages have also made it simpler to verify code. So take the example of Rust. Take this simple program. You have an index ec function, which takes a vector, discards the rest if it's not a list of length 2. So if it must have at least 2 elements. Take a snapshot of the first element, you modify the second element, and you want to check that the first element hasn't changed. This assert in particular, if you use a safe Rust verifier, like Prosty or Crusoe, you will verify this without any additional notation and fully automatically. In addition to that, if you want to add first-order logic annotations, like this assert, but also specifications written in first-order logic, you can, and then you maybe have to do some more work, but you will get it to verify. And it's kind of a pay-as-you-go way. So the idea of doing this was introduced by the Prosty people, the Viper people, in 2019. The idea is you can leverage the type system to enhance verification of safe Rust. And then Crusoe later realized that from an idea from Yusuke Matsushita that you can actually just not even have any separation logic involved and still do the verification. So I was saying all this about Rust. Let's compare with C, because there's been a lot of talk about verifying C this week. And it's like we're gonna, for the context of this talk, call it untyped Rust, right? Take this code, it's basically the same code, and you want to verify that the modify function will, you want to check that this assertion holds, basically. It's just not true, it just does not hold. So if you want to verify this, if you want to do it, for example, why does it not hold first, let me tell you. Because you could be accessing the cell before in the array and modifying the thing you think you're not modifying. So if you want to verify this in Cn, for example, which is kind of an accepted verifier for C nowadays, apparently. Well, it is. It's very good, actually. You have to add annotations that correspond to the type system of Rust. And specifically here, you have a mutable borrow of type U32. And that means that if you simplify a lot, it means that you must own the pointer at the beginning of the execution and still own it at the end. Same for the index ec, you must own the vector and own at the beginning and at the end. And you must also probably add some annotations in the middle of your code, because separation logic is hard and automating it is hard. So what we get from this is that users are actually writing the specifications for you. They're writing separation logic specifications because they're giving you the Rust type signature. And in addition to that, this is very, very simple monomorphic Rust code. There's no abstraction, there's nothing going on. And the Rust type system is very expressive, you can do a lot more. And the more you do, and people usually do that whether it's in C or Rust, the harder it is to verify. And in Rust, that doesn't change much because everything gets encoded into the type system. So Xavier will talk about this in a few minutes. So that's the takeaway. Developers change the way they write code, and they write specifications. Some specifications, they write the type signatures, but these are just specifications. It comes back to what Amal was saying. The type system is giving you a lot of information, you want to leverage that. This is big specifications, right? Like, people are finally writing specifications at scale. Developers, not research engineers, not research verification by people. Everybody's writing specification. Of course, there's a caveat. They will do this as long as they have an escape hatch. You want, if you're doing TypeScript, you can always rely on JavaScript because sometimes it's too hard to satisfy the type checker. And if you want to do Rust, well, thankfully we have unsafe Rust so that we can write our crazy double linked lists that are recursive or whatever. So in the code I showed earlier, there was like a hidden lie, which was that this indexing here is actually internally unsafe. So you have a safe signature for that, and internally, it's implemented using unsafe code that can do crazy stuff and is not really checked by the borrow checker. And that could break the type system, meaning that all the nice properties that were leveraged by Crusoe to verify its code could just go away. Very hard to verify, because this index mute here is not only promising that during the execution of index mute you will not do anything wrong, and you will not create UB during this execution, but also that any function that calls index mute in a safe way cannot trigger undefined behavior in the rest of its own execution. Thankfully, that's only 2% of the code. And it's always safely encapsulated, meaning that you can verify it once and then reuse that specification as many times. That's the key idea that we're trying to tell you. It's hybrid verification. So in your code base, it looks like this, with this bit of unsafe code here. You want to verify the safe code with, for example, Crusoe, and you want to verify your unsafe code separately. And at the interface, you want a hybrid specification that is interpreted by both tools, so that you can do the work entirely separately by putting more effort on one side and less effort on the other side. When we started doing this, there was no tool able to do the unsafe part, so we developed Gillian Rust. Doesn't mean that this is the tools you should be using to do this approach. It's just that we happen to have a prototype that does this using these two tools. And so ultimately, if in average you have a certain amount of effort to provide to prove your code in C, in Rust you should be able to provide a lot less effort for safe code, and maybe more effort for unsafe code where it's a tiny portion of the code. So the rest of this talk, Xavier will be talking about going further in verification of safe Rust thanks to these properties, and I'll come back to talk about what Gillian Rust is doing and how we managed to do this.
All right. Yes?
I wonder if you'll say a little bit about Varus, which is also supporting unsafe using Ghost.
Varus cannot verify real Rust code. You have to implement, Varus is more like, well, it's less and less true, but it's more like a DSL for verification embedded in Rust. You have to, if you want to verify linked list, you cannot verify the standard library linked list. You have to re-implement your own linked list using the Varus standard library to be able to verify it. And in that sense, it's not achieving the goal we're trying to get to. I think that makes sense.
Yes?
So something you said a moment ago jumped out at me. The juice, what was it? It was crazy things like doubling linked lists. So I'm coming more from a systems background, who also does more methods, but doubling linked lists come back crazy.
No, and we can, that's actually one of the easy ones to verify, of course, even in unsafe Rust.
Right. So, I mean, my question was getting on to, to what extent are some things like things that are hard in separation logic affecting what you're tackling?
So, how is what's hard in separation logic affecting this? Well, it just makes the unsafe part harder. But yes. Supposedly, the safe part will not change because we'll explain this later. But you abstract over what the separation logic is doing anyway, and you don't see it ever.
Okay. My question was more. Perhaps we can come back to this afterwards. It was more about the impact on what people specify, what they verify, and what they build, based on what's easy or hard to express in your formulas. What affects society?
To be clear, the doubly linked lists are hard, cannot be expressed in the Rust type system.
Yeah.
Easy to do
Yeah.
separate.
Well, doubly linked list you can do in the Rust type checker with GoCell,
Yeah.
but or you can do it in horribly inefficient ways by putting an arc in every node. But
Yeah.
GoCell is a nice way to do it, I would argue.
Yeah. So you can use things like GoCell, but then GoCell requires you to encapsulate everything within a series of nested closures to get to build your Ghost cells, right? So you can't build the same exact API that you would have for the linked list type in Rust.
Perhaps we're getting more
Yeah,
down the
yeah.
rabbit
Maybe
hole.
we can talk about this afterwards.
I have a different question. Can you go to your example? So, the fact that you can prove that a circle doesn't fill doesn't only rely on the fact that index mud correctly encapsulates and safe code, but it also really relies on some axioms of index mud.
I mean,
so I guess that tools like Crusoe or Prusty or so, they have some axioms about index mud and functions like that.
Yes,
Definitely.
We want to prove them.
yeah, we want to be able to prove them, right? So Crusoe and Prusty and tools like that will have a specification they give to index mute, but that specification has to be trusted by the tool. And the point is that we want to build the tool on the other half that can prove the specification Crusoe expects for index mute.
Okay, so it means you have to establish two things about something like this. One is it correctly encapsulates and safe code.
Yes.
The kind of thing that Rust Belt already did.
Yes.
And the second thing is that it satisfies the kind of things that.
Yeah, and that we can give a nice first order.
And Rust Belt already, I mean, only did it on a model in Conk, not on real Rust also. And then refine Rust, but it's a different question, but we'll get there. Yes.
Could we please see the next slide?
Yes. Right. So the point is, so we have this little example here with a very simple call to index mute with a vector of U32s, etc. This is, of course, very, very simple in the Rust type system. We can do a lot more things at a very basic level. We have generic types in Rust, right? So we can talk about, you know, a very useless modification of a mutable pointer to some type T. And of course, we can write the same kind of code in C, right? So we could use void star and do all sorts of, you know, fun C things to simulate generics in our C programs. But just like before, this gets more painful when we want to specify things. We might need to be able to talk about higher order predicates. So we have some predicate P that describes values of type T, and then that we can use that to describe values of vectors of type T, et cetera, et cetera. Moreover, the Rust type system also has this like trait mechanism, which again sort of allow us to add a bunch of interesting properties to our type. So we can say here, this value of type T is copyable, which in Rust Belt basically means the representation of T is persistent. So we can freely duplicate it. And then reality is in Rust we go a lot further. So the Rust type system also allows us to build really powerful abstractions, like iterators here, where we can do stuff like return series of mutable pointers, apply higher order functions that mutate things, and once again, you know, C is a general purpose language. We can do all this kind of stuff in C, but once again, specifying this kind of code gets a lot harder and a lot more painful, right? And so dealing with higher order code in C, higher order generic code in C gets a lot more painful to specify, a lot more painful to verify. Whereas when we have a strong type system like in Rust, we can actually make this verification really nice and ergonomic to perform. And so to look a little bit more at how Rust actually enables us to do nice verification, even in the presence of higher order mutable, code with mutable captures and things like that, let's look at our little Rust example here. So when we call something like iter_mute, the Rust type system actually provides us a bunch of guarantees. So iter_mute returns a series of mutable pointers to all the elements of our vector v, and the Rust type system will tell us all of those pointers, all of those references are going to be valid for the entire time that we have them. So we're never going to be accessing uninitialized memory. We're never going to be going out of bounds of our vector. They're also going to be unique. So we're never going to have to worry about accidentally having two mutable pointers to the same cell of memory and therefore causing data races or introducing iterator invalidations and things like that. Moreover, Rust programmers care a lot about abstraction, and so they provide these nice interfaces that actually have really strong properties that we can reason about in a generic manner, and thus provide composable specifications. So we can really do things like combine immutable iterators with skipping, with mapping, with all sorts of things like that. And then finally, when we apply something like for each, which is just another version of map that ignores this result, and only looks at the side effects. Once again, the Rust type system really helps us out here because the Rust type system will effectively track what is the footprint of the closure that we passed to our for each. We're guaranteed that whatever the closure captures won't be modified by any any code outside of the closure, so long as that closure is alive. And additionally, again, we get guarantees on the liveness of the values that we have captured, the non-aliasing properties of any mutable state that we have. And so this means that in Rust, the code on the left-hand side can actually be verified fully automatically with no additional specifications in a tool like Creusot. And this is really made possible by the fact that the Rust type system encourages this strong encapsulation, right? So that safe code doesn't have to reason about memory layouts. It doesn't have to worry about bytes and provenance and pointers and all this stuff. We can really reason at the level of mathematical abstractions and go really far, really fast. And this is, what we want to leverage through hybrid verification. Have, for the 98% of the code that is safe, do this kind of fast reasoning. And then Sacha is going to show how for the 2% of code that is unsafe, like the implementation of itermute, we're going to actually need more powerful tools to reason about how those little bits of code actually modify the pointers and create an actual pointer to things in memory. Go ahead, Sacha.
Yes. So, as we said, we need a tool to validate the Creusot specification. As you said, it's not just the safety, it's also the pure side conditions on top of that. First step to do this is to require formal characterization of what the specifications mean in separation logic. And thankfully, there's already work that did this, Rust Belt and Rust Hornbelt. Previous work that was not involved with me, Xavier did Rust Hornbelt. And the problem is that those are meta-theoretical tools. They're models in Coq to model Rust. They don't work on real Rust. That was until refined Rust, and I will come back to this also. And we would also like to have some level of automation and performance when doing this verification and see how much we can leverage the fact that we're only doing unsafe code. So to that end, we developed Gillian Rust. I'm going to talk quickly about what Gillian is for the context that it helps. It's a compositional summary execution tool in the line of very fast, Viper, Java 2.0, and the latest one is CN. The key feature of Gillian is that it's parametric on what we call a state model, which provides state updates like load and store for most languages or alloc or whatever, and core predicates like the points to predicates. And so we have 4 languages right now in Gillian, including JavaScript, C, and Rust. The other one is just a toy language. And you can imagine that the parametricity helped because, for example, the points to predicate has a very different meaning in JavaScript or in C or in Rust. And so here, of course, we're focusing on Rust. And Rust also has a bunch of exotic things like new lifetime update or a bunch of weird resources that capture lifetimes that are extracted from Rust belts, or prophecy observations that are from Rust Hornbelt. So we believe that we could not have reused any existing tool to achieve this level of automation, and that the Gillian's unique parametricity here enables us to, thanks to this reduced scope of problem of only verifying unsafe Rust, create tailored automation here. So Gillian Rust comes with a lot of nice goodies. First, a model of the heap that is compatible with the fact that Rust does weird things with layouts, and also compatible with polymorphism. We're encoding some of the lifetime logic and automating some of that. And actually, if you look at the refined Rust paper that came out, so it was parallel work, but they actually went and modified Rust Belt to improve the meta theory for automation, and it's actually pretty impressive. But we did not do that. We just stayed at the Rust Belt's old version. We also have some automation and encoding of prophecy reasoning that is necessary to reason about Creusot specification. We'll talk about this in a second. And a front end to interpret and reason about the Creusot specification. So let's look just at this. And this is a Creusot specification for the push function in a vector, but actually it's the same specification exactly if you want to push at the end of a linked list. It requires that the vector length is less than usize max divided by 2. It's an actual requirement of the standard library, but nobody will ever have a vector that big. And it says that when the lifetime expires, the content of the vector is its content before execution with the value added at the end. So it's kind of prophetic legacy. It talks about what happens when the lifetime expires. And on top of that, you have the types, which are implicitly part of the specification. So as I said, in this hybrid approach, the safe part does not know what a vector is. It would be the exact same specification for a linked list. It would work exactly the same. Only knows that the pure representation of a vector is a sequence of values, and you only have to reason about that. So how does GNRust interpret this spec in our hybrid approach? Basically, the types become ownership predicates, just like what Amar was doing in the ABI, and what Rosbart was doing also. And then you have the pure side conditions, which are in prophecy, observation things. You don't have to care too much about this. And so it's important that these ownership predicates are not only specifying how the value is actually represented in memory, but it's also connecting the separation logic grungy reality to this pure world of nice abstractions. So basically, GNRust can reason about what a linked list or a vector or whatever is using this complex separation logic invariants or even more complex structures. And then this is lifted to an abstraction world where Crusoe can reason about, and for Crusoe, a linked list is just a sequence of data that has pure values. And this is really what makes hybrid verification work. So the last ingredient we need now is targeted automation so we can automate and improve performance on verifying just unsafe code. And again, it's enabled by the fact that we have Jillian and we can create our own automations and customize the tool. And hybrid verification, because the scope of the problem is a lot smaller, we only have to verify unsafe code. So this was the specification we have. This is the actual code of push from the standard library. And there's a lot happening, so this is more for those who know how you verify Rust or C code. So there's this notion of opening and closing borrows that we can automate. It says basically that when you receive a mutable reference to a vector, you have to kind of open the invariant to access what the vector is, and at the end you have also to reestablish the invariant of the vector before the lifetime ends. And this is not specifically said in the code. So it's kind of ghost operations. In Jillian, unspecified functions are just executed, so that allows us to reduce the overhead in writing specifications. And in particular, internal functions often do not really have nice specs. So we just execute them at simple execution runtime. Pointer arithmetics and byte reasoning is automated a lot thanks to the M30 solver and the heap model of GNRust. And specifically here for pushing at the end of a vector, there's absolutely no annotation to add to make the vector and array reasoning work. And finally, we still have sometimes custom annotations and tactics that are required. And here, this is to resolve the prophecy, so I will not go into details, but this is something we haven't managed to automate yet, even though I think we can automate it, but let's see. So once you've done this proof, which is just one line of tactic, you can verify, and we can, for now, verify all of this in 2.7 seconds, which is I think our slowest benchmark, but VEC is quite complex. But once you've done that proof, then you never need to reason about the representation of a vector anymore. Crusoe can only reason about its representation, and that's what our hybrid approach is.
All right. Yes.
So can you verify most of this Rust standard library implementation?
It would be nice, wouldn't it?
Yeah, then we'd be done. How far are you?
Oh, we're very at the beginning. GNRust is GNRust is a prototype.
How far are you? Like, is it
The big one
about capturing all sorts of patterns?
So far we have only done data structures, linked list, vector, for the standard library. I think what else do we have? I could look at the benchmark. It's not an archive yet.
I think in terms of language support, the biggest thing that's lacking is concurrency, right? So that's the real limitation, I would say. So we can't do mutex, we can't do atomic stuff yet.
Well, in the context that's what we have is valid in a concurrent context because it's separation logic, but we cannot do concurrency primitives. But also dumb things like the Rust compiler is a bit difficult to work with, and we cannot even get properly the lifetimes in specifications. It's difficult to differentiate because it's erased before at this time.
It's all implicit. So
Yeah,
yes.
and it's erased.
So we had to recreate that information. And
So this is like a lot of engineering that needs to be done.
Yeah.
But also, like Refine Rust, Michael is here. Refine Rust is also doing a lot of things to automate, to improve what you can do and how you can automate it. So this is also getting us closer. But yeah, we're very far away from verifying the standard library.
Yes?
This is why you need prophecies to verify index root.
That's mostly because the way Crusoe reasons about things like programs that consume mutable borrows or return mutable borrows is using prophecies. So these are prophecies in the style of Rust Hornbelt, not like the future is ours, Iris prophecies. And basically it's just reasoning about future values of things, using the uniqueness of mutable borrows to guarantee that you're allowed to do that and it's safe. On the other hand, it makes verifying that unsafe code a lot harder.
Finish the takeaways.
Right. So basically, I mean, the appeal of what we're trying to do is that the vast majority of Rust code out there is sort of doing boring safe stuff. And so we shouldn't have to worry too much about the complexities of the tool we use to verify them. And with techniques like what Prusi does, what Crusoe does, what Varus does even for the safe fragments of Rust, we don't have to do that. We don't have to worry too much about that. We can really reason in terms of mathematical abstractions. But of course, you know, there is unsafe code out there. It's important, it's at the foundations of everything. And that code tends to be more complex, so we can use sort of highly calibrated tools that are specified, that are designed to verify that small portion of code, like Jillian Rust, so long as they're able to communicate through the specifications that lie at these boundaries. And as we saw yesterday, you know, easy code should be easy, complex code must be possible. And our argument is that with hybrid approaches, we can really make easy code easy and make complex code possible. Thank you.